Everybody sits down and stop talking. Thank you very much. Okay, this is an action potential of a neuron. Only neurons will have after hyperpolarization occurring. So this here, this after hyperpolarization, you're not going to see that in any other excitable cell, only in a neuron. So when you get to muscles, don't look for it. It's not going to be there. Resting membrane potential in muscles will be different than neurons, minus 90. Threshold will still be in the positive direction, probably 20 millivolts, maybe 15 to 20 millivolts. So instead of minus 50, be minus 70. You have the upswing, the action potential looking pretty similar in the muscle. The repolarization goes right back to resting and flatline. No after hyperpolarization. You get to cardiac muscle cells next semester, and you got all kinds of different shapes for action potential. You have all kinds of different ions moving. So, as I said before, learn the simple version now, because it's just going to get more complicated later. So, action potential, less than 1 millisecond, boom, it's over. After hyperpolarization is not really considered part of the action potential. It's preventing another action potential from being generated due to events that are going on downstream, and it's making any input to the cell have to be larger to get the action potential generated. So you have to make up that negative difference and then get the positive charge to get to threshold. So you have 10 millivolts of negativity and then 20 more millivolts of negativity. So the threshold is essentially been, the distance to the threshold has been increased by a minus 70 millivolts. So you have to get a plus 10 millivolts more positive charge in there to get to threshold than normal. Whenever you see an arrow down here in the time, that's referring to the arrival of a stimulus. So you could have a single arrow, meaning one event is occurring out here. Maybe all of these neurons that are going to be creating negative and positive, they all happen at the same time. And so you get them, the local potential summing right away. You got to threshold, so you got an action potential. So voltage gated channels are not ligand gated channels. Voltage gated channels open because charge arrives. And you reach the threshold to open the voltage gated channels. Sodium channels will open when you reach the threshold of the neuron. And potassium channels, voltage gated channels, will open when the action potential reaches its peak, around plus 30. That's when potassium channels start opening. So it's charge. You get to minus 55, minus 50, you get that much positive charge coming into the cell, you get a voltage-gated sodium channel opening. In order to get a voltage-gated potassium channel opening, you've got to get to plus 30 millivolts. So much more charge to open a potassium channel. But you wouldn't want to open potassium channels earlier at a more negative membrane potential on the rising phase. Why? Why don't you want to open potassium channels before sodium channels close?
Because the potassium doesn't flow out, making the things that are negative.
Yeah, then you got to get more sodium in. So it's gonna counteract what you're trying to do with the sodium channel. You can open potassium channels a little later than the closing of the sodium channels, but you can't open them before sodium channels close. Otherwise, you got positive charges going out and you're gonna have to get more positive charge come in. So it's pretty logical. I see faces out there going, yeah. Okay, if it's yeah because you got it nailed, fine. But if it's yeah because I don't want to think about it right now and I'll think about it before the next exam, too late. Okay, sodium channels have 3 conformations. The first conformation is when you can excite it. Right now, sodium is prevented from coming in because there's not enough change in charge inside the neuron to get this channel to activate its, or open its activation gate. So sodium tries to diffuse in, but it has to stay outside. When you get enough positive charge at the trigger zone coming into, well, first when you get enough positive charge arriving at the trigger zone, you get the sodium channels to open. When sodium comes in and diffuses to the next region, then you get the sodium channels opening in that region. When sodium is coming in through the channel, positive charges accumulate inside the cell and cancel the net negative charge that was in there during the resting phase of the cell. Positive charge leaving the outside leaves net negative charge behind. You have now reversed the potential across the membrane. So it doesn't take a lot of sodium coming in to get that reversal, because a sodium coming in cancels the negative charge inside, and its absence outside leaves net negative charge outside. So very little sodium actually has to move. When the positive charge accumulates inside, it pushes this ball into the channel. The negative charge that's accumulating outside attracts that ball into the channel. So there must be positive charges on that part of the protein. You read your book carefully and it says accumulation of positive charges repels or pushes the inactivation gate into the channel. Has to be plus interaction, right? So charges repel to push the ball into the channel. When it gets close enough to the channel that the positive charge can interact with the negative charge outside, then that is an attractive force to move the ball into the channel. This closed inactivation gate is going to remain closed as long as you have positive charge excess inside the cell and negative charge excess outside the cell. What is going to correct for that?
Pumps.
The pumps. So when in doubt, ask Eric. He's going to say the pumps to anything you ask him now. What's your name?
Eric.
Thought maybe he'd say the pumps. Okay. Okay, he's the pump man. Okay, so when the pumps pump the positive charge back out, 3 sodiums go out, 2 potassiums come in, but overall you start getting more positive charge out, and the outside now starts to become positive again. The inside becomes negative again, and you're back to resting membrane potential. If potassium channels that are open when you hit the peak of the action potential are still open, you'll go past resting into the after hyperpolarization phase. That only occurs in neurons, not in any other excitable cell that they've identified so far. So positive charge accumulating inside the cell is going to cause these channels to open. So you gotta have your membrane potential at plus 30 millivolts at the height of your action potential for these channels to open. When they open, then potassium leaks out very quickly, and the membrane becomes even more negatively charged inside and more positively charged outside. This is bringing the inside of your cell back towards the minus 70 resting membrane potential. These stay open longer than they need to. The muscles have, you can think of them as having figured it out, that they don't need to go into this after hyperpolarizing phase. But you can also think, well, the nervous system doesn't want to have inappropriate firing of action potential. It wants to control what messages are going out and not have too many signals going out and fatiguing your effector cell. So if the next stimulus is not greater than the previous one that set off the action potential, the cell simply doesn't respond. It sets up mechanisms where it won't respond to backflow of positive charge from downstream voltage-gated sodium channel opening. You don't want this continuing firing of your nerves. You're going to run out of energy. You're going to be a blob on the floor if that happens. So, positive feedback. When positive charges come in, they open channels that allow positive charge to come in the next segment. When that positive charge comes in, it diffuses downstream and opens channels that allow positive charge to come in the next segment. So when you have a depolarizing local potentials that sum to threshold at the trigger zone, you then open voltage-gated channels. Sodium comes in. As sodium comes in, the membrane potential will go in a positive direction. When you open, when the membrane potential goes in a positive direction in that local segment of the axon, you can open the next voltage-gated channel. So decrease in membrane potential is decreasing towards threshold. Don't think it's going more negatively. So it's a little perverse, I guess, a little confusing if you think of decreasing as going in a negative direction. When you talk about something getting more negative, you talk about an increase in the membrane potential. When you talk about a decrease in the membrane potential, you're getting less negative, and going towards threshold, you're going towards zero. Okay, so let's just write that down. So a decrease in resting membrane potential, you're actually going towards threshold. So your resting membrane potential is going in the positive direction towards 0 millivolts. An increase in the resting membrane potential. You're going from minus 70 towards plus 0, towards 0. This is going in the opposite direction. So resting membrane potential increasing, you're going more negative. Decreasing, you're getting less negative, going towards 0 millivolts. So when you look at this slide, it says depolarization decreases membrane potential. It's going in the positive direction. Go back to slide number 1 and look at the depolarizing local potential. It's going towards 0. That's due to positive charges coming in through the voltage gated channels. When the voltage gated channels open, positive charge enters. When positive charge enters, you get a decrease in the membrane potential towards 0. That's for sodium channels. If these were potassium channels that were opening here, then potassium would be effluxing. It would be going out, and that would increase the membrane potential, and that would be a hyperpolarization. Got it? 1 person, 2 people, okay, 3 people, 4 people. All right, got some bobbleheads out there. Good. Okay, so this is summarizing all the events with voltage gated channels. At resting membrane potential, all channels are closed. All voltage gated channels are closed. Leak channels are still open. So sodium leaks in, potassium leaks out. ATPase, or Eric the pump man, is there pumping sodium out and potassium back in. When you sum your graded potentials from your dendrites and your cell body, and you get to the threshold of that neuron, here it's minus 50 millivolts. At that point, your activation gate in your sodium channel opens. Sodium rushes in. The sodium accumulates very quickly, and instead of this curve here, you got almost a straight line, straight up. At the peak of the action potential, that's where there's enough sodium inside the cell to push the inactivation gate into the channel. So positive charge repels it up, and negative charge outside attracts it up into the channel. So P is talking about permeability. So arrow going up, increase. Arrow going down, decrease. So increase in P, they're talking about permeability of sodium. Permeability is going up because you've opened these voltage gated channels. The permeability to sodium goes down when the inactivation gate swings into the channel. At that point, potassium permeability is increasing. What's happening? Potassium channels are opening. Potassium is going out. It's leaving the neuron. That's an efflux of potassium. The potassium channels stay open, and potassium is diffusing out. You see a problem here? It says potassium out, falling phase stops at resting membrane potential. Wrong. It continues to efflux and cause the after hyperpolarization. Potassium channels close here. So the falling phase is primarily due to potassium, yes. My inference here may be wrong because they do say it closed, potassium channels close here, but I would have my bracket over to there. In my mind, it makes more sense if the falling phase goes into the after hyperpolarization phase, because it's not that it's there sometimes and not there other times. It's always there, and it's always due to potassium leaving the cell. after hyperpolarization phase is because of the potassium channels being open longer than needed to get back to resting membrane potential. In a neuron, that is very significant in the function of the neuron. It prevents just normal levels of stimuli from reactivating that neuron. You could reactivate these channels now because when you've gotten back to resting membrane potential, at least according to this textbook, you have, it's implying that all your sodium channels are now back in their original conformation and can be reopened again. So having potassium still leaking out at that point is ensuring that the sodium that's entering downstream is not setting off another action potential upstream. You have to have more sodium upstream coming in to get to threshold because of that after hyperpolarization. You've taken the whole inside of the cell further away from threshold by 10 millivolts. To get back to threshold, you've got to have the original 20 millivolts of positive charge, and now an additional 10 millivolts of positive charge. So it's buying some time, it's controlling the output of your nerves, preventing them from overstimulating whatever is downstream, another neuron or muscle cell, and so you're not twitching away there, but you're able to control the activation and get smooth muscle and smooth contractions of your muscle. So what allows the sodium channel to go from inactivation closed to activation closed, inactivation gate open, sodium potassium ATPase, pumping positive charge out, positive charge leaking out the open potassium channels. As the cell becomes more negative inside, this part of the channel protein will then open again. It will be attracted to the negative charge. As the positive charges accumulate outside due to the sodium potassium ATPase and potassium voltage gated channels, this part of the protein is repelled out of the channel. And there will be charge-charge interactions that will close the activation gate. So this is just stepwise. This is resting membrane potential. Nothing has happened. Next step, you have graded potentials that have got you to threshold, and then your voltage-gated sodium channels will open. Next level, sodium rushes in till you get 30 millivolts of charge inside the neuron, positive charge inside the neuron. And then voltage-gated sodium channels close and voltage-gated potassium channels open. So sodium's not coming in, ATPase is pumping it out. First part of repolarization. Permeability of potassium going up causes the repolarization phase, the falling phase, brings you back to resting membrane potential, where according to this textbook, your sodium channels are now ready to be reopened again. So theoretically, if you restimulated the nerve at that fraction of a millisecond, you would then be able to generate an action potential again. But how short is a millisecond? And this is like 1/100th of a millisecond, or even 1/1000th of a millisecond. Highly unlikely that everything's going to coincide there. Any time sooner, you don't have enough sodium channels to open. Any time later, then you've got the potassium channels still letting potassium leak out, and you need more sodium to come in to get back to threshold. So relative refractory period there, meaning you only can get another action potential generated if your stimulus is bigger the second time around. And that's not going to happen downstream by opening the next bunch of sodium channels. So it keeps action potentials propagating in one direction. If you re-stimulated the membrane upstream, it might start sending action potentials back to the cell body and the dendrite. It's a waste of energy because it's not going to have any effect there. You don't have any neurotransmitter to be released there. It's all downstream. So having the action potentials go in one direction only keeps your nervous system efficient. Again, no decrement in action potentials, all or none. You get it or you don't get it. Going from sodium channel to sodium channel, that's and opening it, that's due to a local graded potential that's depolarizing. Having potassium leave creates a local hyperpolarizing potential. So both these events with sodium and potassium are occurring in the axon as well as the dendrites and the cell body. So this has a summation of all the things that we talked about. The summation is what's occurring out here. You can sum by stimulating one neuron many times and just keeping a channel open. Maybe use some depolarizing events. You could also sum hyperpolarizing events. When you repetitively stimulate one neuron, that's referred to as temporal summation. When you have multiple neurons stimulating either for depolarizing or hyperpolarizing events, and those events are occurring over the surface of the cell, that's referred to as spatial summation. So simultaneous stimulation over different areas of the cell would be a spatial summation. If it's one neuron that you just keep firing action potentials to keep those channels open, that's temporal summation. We didn't talk about that, but everything else we pretty much discussed. The duration of the action potential will vary. You could have some neurons that have action potentials that are more stretched out. That's going to be due to how many potassium channels are opening, how fast you repolarize, other events that are going on. So you can look at this, but your emphasis should be on what we've discussed in lecture. And if you have questions, you can always ask me or email me, do I have to know this now? And I'll tell you, well, not yet, you'll have to know it at the end of the semester, but not right now. So refractory period, got two of them. Absolute refractory period means you absolutely positively cannot get another action potential at this time in that neuron based on the charges that are flowing into the cell. Pretty much, if your sodium is coming in and all your channels are open, you're not going to be able to use them for another event. When you close them and can reopen them, and your potassium channels are closed, there's no hyperpolarization going on, then you are back to resting membrane potential. Between the time that you close sodium channels, open potassium channels, somewhere in that falling phase of the action potential, if you have a bigger stimulus and you get the sodium channels reopening and you get to threshold, then you have gone into the relative refractory period. So there's a time when sodium channels are closed, potassium channels are opening. You can get another action potential triggered at the trigger zone, the axon hillock, initial signal, but it requires a bigger stimulus. That's when you're in the relative refractory period. So relative, you can re-stimulate the nerve, but you need a stronger stimulus. Absolute refractory period, nothing you do to this neuron is going to get another action potential generated. The absolute refractory period and relative refractory period make it highly unlikely that action potentials are going to be generated upstream, except from that trigger zone due to another stimulus, a wave of stimulation coming into the cell body and the dendrites. Anything that's occurring downstream in the axon is not going to cause another action potential to be generated to travel upstream. It's going to continue to go downstream. You're running into that after hyperpolarization upstream. So backward current flow, it is canceling charges here, reversing the membrane potential, but only the forward current flow is actually going to open voltage-gated channels. This backward positive charge is running into negative charge upstream, big time negative charge, 10 millivolts of negative charge upstream. Not just a little bit due to resting membrane potential, but a big negative charge upstream. So it's not going to be generating backward action potentials. Only that forward current will run into channels that can reopen with that magnitude of positive charge. So permeabilities, we've got our action potential in red, we've got sodium in green, and we've got potassium in blue. At resting membrane potential, permeability to sodium and potassium is at baseline. Got some leak in and out, but the pumps are correcting for that. So there's no change in the membrane potential due to the movement, that passive movement of those ions. When you get to threshold, then sodium opens very quickly and permeability goes up, so does the rising phase of the action potential goes up. When sodium channels close, then you're at the peak of the action potential. Sodium permeability is going down and you're now repolarizing. You're in the falling phase of your action potential. If you come down to potassium, when sodium channels close, that's when potassium channels are opening. Permeability to potassium goes up and remains elevated even after you've reached resting membrane potential. Potassium efflux is still high, very high. As you get to a more negative state, now potassium wants to stay in, even though the voltage-gated channels are open. Less of it is leaving through the channel because it's got an electrical gradient to stay in. Part of the reason why potassium moves out so fast is because you got all that sodium inside and positive charges repel. So as you pump sodium out and there's less positive charge inside, potassium, the slope starts to get a little flatter at the point where there's not enough positive charge to inside to keep these channels open. So potassium channels close and now the efflux is decreasing. So positive charge starts to accumulate, and you start going from minus 80 back to resting membrane potential. So as permeability decreases for potassium, your charge inside your neuron starts to go in the positive direction again. You're starting to accumulate potassium inside the cell. So all or none principle, you get action potential or you get no action potential. The frequency of the action potentials vary with the neuron. How many of you saw the video in lab today? How many remember that you saw the video in lab today? 3 people, 4 people, okay. There are some neurons, you increase the stimulus and they go boom, boom, boom. They fire at their own rate, even though you're just shoving electrical charge into the neuron. The refractory period is very long in those neurons. So they don't fire but every maybe 10 milliseconds. Others, you start dialing up the stimulus and they start to fire more often. They fire more, less frequently as they're being stimulated for a longer period of time. They kind of poop out. So they get big bursts of action potentials and then it becomes less frequent. So the frequency of action potentials depends on the type of neuron that you're dealing with. When you have neurons that are sending information that's very important, like pain, that you want to avoid that painful stimulus, they send a lot of action potentials in a very short period of time. Others that are, okay, I sat down in the chair and I made it into the chair and now I don't even realize that I'm sitting on the chair anymore. Your brain is not getting any information about that. Part of that's related to the type of receptor you have and also the fact that the receptor is now turned off and the neuron is also turned off by this constant stimulation. Okay, time to quit. So next week